All right, ladies and gentlemen, class recording has begun. We are going to start today in your book on page 100. So if you have book, open up to page 100. And on page 100, we are going to start with question number 54. So page 100, problem number 54. Problem number 54 says, one fine summer day, a group of students were jumping from a railroad bridge into the Snohomish River. Last period, we tried to figure out where the Snohomish River was, but apparently that fell through. So maybe at the end of the period, we'll find out where the Snohomish River actually is. It says, they stepped off the bridge when they jumped, and they hit the water 1.5 seconds later. How high was the bridge? So, first things first. What is this question asking us to solve for?
Height of the bridge.
Okay, height of the bridge, right?
But that's pretty much displacement.
In terms of our equations, right, height of the bridge, that's going to be the displacement that these kids or these students fall after they step off the bridge. So, indirectly, it's asking us to solve for the displacement of this object, these objects under the influence of gravity. Okay? Now, they've asked us to solve for displacement, and earlier in this chapter we would use a kinematic equation to solve for displacement. But we said that kinematic equations are only valid under certain circumstances. Do we remember what has to be the case in order for us to use kinematic equations? Constants, acceleration. And because these objects are going to be under the influence of gravity, that is a constant acceleration. So kinematic equations will apply here. So we've now figured out what we're looking for. Now we got to come up with three pieces of information that we know. One piece of information is pretty obvious from the problem. And what's that going to be? Okay. It tells us that it takes 1.5 seconds in order for these kids to hit the water below. Okay? Next, we need two more pieces of information. Actually, what else?
Acceleration.
Acceleration is going to be what in this problem?
9.81
Because?
That's what gravity is.
Okay. Acceleration is going to be 9.81 meters per second squared because gravity is causing these objects to move towards the water, and that's the acceleration caused by gravity here on Earth. Okay? Two pieces of information. What's the third one?
Initial.
Okay, so it tells us that these kids just stepped off the bridge. That's the equivalent of us taking a ball and just sort of dropping it from rest. Okay? At that instant that they step off of the bridge, they're not moving. At that very instant when they leave the bridge, they will start accelerating immediately. But at the very instant that they leave the bridge, their velocity is 0. And that means the initial velocity of the objects in this problem is equal to 0. Good there? Okay?
What's the equation again for this?
Well, look on your chart and find out. So now we've got one thing we don't know, three things we do know. Now it's a matter of picking the appropriate kinematic equation that has those four things in it. And when you do, you find out that it's this equation that has the three things we know and the one thing we don't. So now it's a matter of plugging in things that we know into this equation. Delta x's are unknown.
Will that be over there when we're taking tests?
Yes.
Thank you.
But you will also have a note card too, so it might be a good idea to write those equations down on your note card, you know. Delta x's are unknown, so that stays there. You don't have to show me this, but just because this is the first time we're doing it here, right? The initial velocity is 0. The time is 1.5. 1/2 is part of the equation, right? So that just stays 1/2. You can't change that. The acceleration we already established was 9.81, and then the time 1.5 seconds, but remember, we got to square that value, just the time, not that whole term, just the time. And you plug that in.
Yeah, 11.
And you should get
11.4 actually.
11.03,
6.
okay, which we're going to round to 11 anyway, so 2 sig days. Okay. Julie, go ahead.
For the test, can we just put 11 meters, or do you want us to put the answer and then put the answer in sig days?
If you put 11 meters, that will be fine, okay? I try and do it like this when I'm doing examples, Julie, so you can see, like, that's what this is what my calculator gave me, and that's how I rounded it. Just so if you don't get, when you plug it into your calculator, if it doesn't come up to say 11, you don't think something's wrong. Why didn't I get 11? Okay? Yes, Maxie?
Wait, how come you know it's 2 sig digs?
2 here, okay? This is a constant value, but so we usually kind of disregard that, right? But it's 3 anyway, right? And then here, even though I only wrote 0 as 1, it's really 0.00000000 because it was exactly 0.
Okay.
You know what I'm saying?
Yeah.
So we can just kind of disregard that as well. So we'd go with 2 then.
Okay.
Good there? All right. Next, turn to page 101. So next, let's turn to page 101. And on page 101, we are going to look at problem number 61. So, page 101. All right. Page 101, it says, a volcano launches a lava bomb. A volcano launches a lava bomb straight upwards with an initial speed of 28 meters per second. Taking upward to be the positive direction, find the speed and direction of the motion of the lava bomb 2 seconds and 3 seconds after it is launched. So before we get into doing this problem, I'm going to draw myself a picture that looks like this, and there's my ground. And I don't have brown, so I'm going to make my volcano just black. Alright? And then we'll add a little lava coming out the top. Right? But more importantly, right? There's our lava bomb. Okay? Alright. So, we'll address that in a second. First, what is this problem asking us to solve for?
Velocity.
Which velocity? Final velocity, right? And we know that because it says speed and direction 2 seconds after it's launched, right? So for part A, we're looking for V final. And it already told us that we're looking for V final specifically 2 seconds after that lava bomb gets launched. Okay? Good there. Now, getting into the things that we know, what else did they tell us in this problem?
Acceleration.
Okay, they didn't exactly tell us the acceleration, right? But we know that, let's go with this first, right? It tells us here that the initial speed was 28 meters per second, right? But initial speed isn't one of our isn't one of our variables, right? What is the variable that we use? Initial velocity, right? And we know the difference between speed and velocity is what? Direction. So we know that this is 28 meters per second, but in the problem they told us that upward is the positive direction. So before we set up our directional system, what should we do first?
Label.
Label what?
Positive.
Before we do that, before we set up the directional system, we should pick something first.
Equation.
Nope. Point of reference. Dylan, what do you want the point of reference to be in this problem?
Top of the volcano.
Top of the volcano is a great place to call a reference point, right? So there's our 0 point, right? That being said, now we can go, all right, we're going to call up positive, and then if we call up positive, that means that down's going to be negative.
So,
Okay?
I have a question.
Yeah.
So if we see this on the quiz.
Yep.
My first reaction would just be 28 minus 9.8 times t, and then just use that as equation. That would work.
Well, hold on a second. Let's finish doing these variables, and then we'll go, right? Really, how you solve the problem depends on what variables are there to work with and what you're trying to solve for, right?
Yeah.
Because that determines what equation you're supposed to pick to get what you need to get to. So that's why when I'm doing these problems up on the board, I'm always going to take this stuff first, then we'll pick the equation. Because the information based on what they gave us or what we're looking for and the things they gave us to work with, that really determines what equation we use. So to jump into it before we have all those things, it's not going to necessarily lead you down the right path. Okay? So, in this case here, our initial velocity isn't just 28, it's actually what?
Plus.
Positive 28, right? Then, we know the acceleration. Acceleration is going to be what? Okay, gravity. So it's going to be 9.81 meters per second squared. But which way does gravity pull on stuff? And in this problem, we call down negative. Okay?
So the initial velocity is plus 28.
Yep.
But we said the reference point was at the top of the volcano.
Yeah.
And that's where 0 is.
True. But remember, the velocity tells you, the sign on velocity tells you which direction you're going, not where you are. Right? This is what it's doing, not where it is. Right? That's displacement.
I got you.
Okay? So now, we have a set of information. 3 things we know, 1 thing we don't, right? We go to our list of kinematic equations, and we see that that equation has the 3 things we know in it and the 1 thing we don't know. Now it's a matter of plugging things into that equation, right? And solving for what we need to solve for. Go ahead.
For the time, it's changing time, like the equations.
That's the same. I mean, like, it's the change in time, yes, but generally we start a problem at a time equals 0, you know? So if we make this delta t, it's really 2.0 minus 0. So we just, yeah. Generally that time is going to start at 0. And you can, I would say you're pretty safe in making that assumption in pretty much any problem that we do here.
Unless it makes sense.
Okay? Unless it says specifically, yeah. Okay. Nita, go ahead.
So if the lava bomb was going down, would that make gravity positive?
Hold on 1 second to that, okay? To fast answer your question, if the lava bomb is going down, would that make gravity positive? The fast answer to that question is no. Because gravity always pulls which way? Down. So in this problem, the acceleration from gravity is always going to have what sign? Regardless of which way the lava bomb is going, right? Now, Nina, in this first problem, the lava bomb had a positive velocity, but a negative acceleration. So what happens to the lava bomb in this case? If its velocity and acceleration have different signs, it's going to go up, but what's going to happen to it while it's going up? If they have different signs, it's going to slow down. Okay, does that make sense? All right. So that gets us into a little bit of, okay, what is it doing now, but what will it do next? Okay. All right, the second part of this problem asks us again for the speed and direction of the motion, right? But now it's asking us for 3 seconds after it was launched out of the top of the volcano. The initial velocity is still positive 28 because that was still how it got launched originally. And the acceleration now is still negative 9.81 meters per second squared. Because regardless of how long the flight of that object is, gravity will be acting on it the entire time. So the acceleration will always be negative 9.81 as long as it's still in the air. Right? So, going back to the list of equations, right? This is still the equation that we would use. It's still those three things we know and the one thing we don't know, right? But now when you solve, you should get a negative answer. Okay? Are we good with the negative answer?
This means it's going down.
That means, Bechtel, what happened between the 2-second mark and the 3-second mark?
Stop and change direction.
Stopped, changed directions, started coming back down, right? Does that make sense?
Yeah, that makes sense.
Good. So yeah, the fact that this velocity was positive and now this velocity is negative, that means that that's what had to have happened during that time between the 2-second mark and the 3-second mark. It hit its peak, started coming back down. Okay?
Okay, so this is just based on like physics. I just have a quick question. You shoot a gun straight up in the air, and then it goes all the way up and then comes back down. It should hit you the same as a like shot. But what about air?
Okay. That would only be the case. So that's a good question, Maxie, right? Anything that we throw into the air is going to come back down. If gravity is the only thing acting on it, it should come back down at the same speed that you threw it. But is that ever really the case? No, because we have to deal with things like air resistance and stuff like that. Now, is air resistance going to slow a bullet down a whole lot? Not really. Bullets are made to sort of be air resistant or resistant to air resistance, right? So it's still going to be coming down pretty fast. That's why if you're prone to do this, you shouldn't shoot guns in the air in celebratory gunfire, okay? Because that bullet comes down somewhere, right? Okay. Julie, go ahead.
How do we know when we would label gravity as negative?
Okay, that's a good question. All right. So, hey, so just for the sake of the recording, I'm going to repeat your question, right? So, how do we know when we label that gravity negative? Julie, it depends on which direction you called positive and which direction you called negative in the problem. Gravity's always going to pull which way? Down, regardless of what we call it. Okay? So that whether it's positive or whether it's negative depends on how you set up this frame of reference to begin the problem. Does that make sense? Okay? So yeah, it's always pulling down, but whether that's positive or whether that's negative depends on what did we decide at the beginning of the problem to call up and what did we decide to call down. Does that make sense?
Yeah.
Okay? Back to a question, go.
Does gravity change with elevation, or is it just always?
Slightly, yes. But
Does that mean that if you shoot a bullet high enough that because the earth is spinning too, like it would change, it wouldn't come straight back down?
technically, no, because it would still come down in the same spot, but because when you fired it, the earth was moving with you, So that bullet was actually moving sideways when you shot it straight up in the air because it was turning with the earth. So just like I think we talked about this here in this class, right? The ball, yeah, same idea. But let's finish this last problem, then we can discuss that. So, all right, are we good here? Okay, last problem for today is on page 108. Page 108. And on page 108, there's question number 121 about lava bombs. Hey, it's like a lava bomb kind of day. So, all right. So it says a volcano shoots out blobs of molten lava called lava bombs from its summit, as shown in Figure 3.33, which is shown below. A geologist observing the eruption uses a stopwatch to time the flight of the lava bomb that is projected straight upward. If the time for it to rise to its maximum height is 2.38 seconds, and the acceleration is 9.81 meters per second downward, what was its initial speed? So, first things first, what are we looking for here in this problem?
Initial speed.
Initial speed, which really we're going to call initial velocity. Okay. All right, let's take care of obvious things first, right? What's one piece of obvious information they gave us in the problem?
Height.
No.
2.38 seconds.
Okay, so they told us that the flight that we're concerned here is going to be 2.38 seconds. Okay? What other information did they give us?
I know the last year's the way to
Okay, let's save that one for a sec. Let's save that one for the end, Julia, okay? What's the other obvious piece of information they gave us here in this problem? Okay, they gave us the acceleration, right? Acceleration is 9.81 meters per second downward, okay? So Julia, like we kind of just talked about, right? In this problem, even though they didn't specifically say it here, from this picture, they called the top of the mountain the reference point, just like Dylan did in the last problem. And then here, this arrow points upward and it has X at the top of it. That's really positive X, okay? So they've called upward the positive direction, and that means that downward is the negative direction again, okay? So in this case, we know that the acceleration numerically is going to be 9.81, but because it's downward, we'll give it that negative sign. Does that make sense?
Oh, because down, oh.
Okay. Yeah, because they kind of, even though they didn't specifically say it in the problem, they called up positive in this problem. Okay. All right. But that's only two pieces of information, right? So, Julia, what's the last thing that we're going to use here? Okay. So, Julia says that V final is going to be equal to 0 because it talks to us about the maximum height. That was a terrible line. So, I'll draw it again. It talks to us about the maximum height. What happens when we throw the ball into the air? Well, eventually, what's that ball going to do? Stop. Where does it stop? At its highest point, right? So, if we're talking about the maximum height of this object, its velocity will 0. That applies on the up trip, right? On the way up, that object slows down, slows down, slows down, slows down, slows down until it eventually stops. That's the top of the motion. After it stops, what does it start doing? Now it starts coming back down. So it's never going to get any higher than when its velocity hits 0. Okay? Good there? And now it's just a matter of going through and picking the right equation, right? And you solve that. So when you solve this problem, you should end up with a positive number for that initial velocity.
Wait, I got a negative.
You got a negative here, right?
Oh, the accelerator. That ran. I did it wrong, yeah.
Acceleration being downward, right?
Yeah.
Means X can be negative. Okay.
Where'd you get 23.3?
So, back to we're solving for this, right?
Right.
Okay. This is 0.
Yeah.
So then here we multiply the acceleration times the time, right? But we're multiplying 2.38 times negative 9.81.
Okay.
So this turns out to be negative here. But to get VI by itself, what are you going to do? Add it to both sides, and that's how you end up with a positive number. Okay? Good there? Okay, so quickly to review. The 3 problems we did. The first problem that we did, right? They stepped off the ledge, or we dropped this object, and that gave us that the initial velocity of this object was equal to 0. So anytime we drop an object, or anytime it just like leaves the edge of something like that, as long as it's not thrown downward or thrown upward, that initial velocity is going to be 0. Okay? The second problem we did dealt with this frame of reference, right? One way positive, one way negative, and that led us to have an initial velocity being positive and an acceleration being negative. And that's okay, right? We have to keep that in mind with which way those things are going in relation to the frame of reference that we set up. And then the third problem we did, we were talking about something at its maximum height. And when it reaches its maximum height on the up trip, that means its final velocity is equal to 0. Okay? So there's a reason why we did these 3 problems. There's a good chance you're going to see something similar to one or all 3 of these problems that's going to show up on your test on Friday. Okay? Good there? All right. You have about 12 minutes left until the end of the period. Here is the homework for this evening. These 6 problems down at the bottom are dealing with kinematic equations of an object in free fall under the acceleration of gravity. Right? So you can take a look at those if you want to see the problem, or if you want to see the answers. I'll show the answers up here in the front. Okay. If you want to pick up your quiz from last week, you can do that back there. Please make sure that people that haven't taken the quiz yet don't see it. Or if there's some other studying, review type things you want to start doing, that would be fine as well. Okay?